Christmas Eve, 2024. The Parker Solar Probe swings around the Sun and reaches 692,000 kilometers per hour. It is the fastest anything human hands have ever built has ever moved. Nearly 200 times the speed of a rifle bullet. At that pace, you could cross from the Earth to the Moon in about 35 minutes. The astronauts of Apollo 11 needed roughly 3 days to make that same crossing. Now take that speed, lock it in, hold it steady for every single second of an entire human life. All 73 years of it. No stops, no slowing down, no pause to sleep, or breathe, or look back. At the end of that lifetime, you are sitting at the very inner edge of the Oort Cloud, the outermost frozen shell of our own solar system. You have not reached another star. You have not reached the halfway point to another star. You are barely 1% of the way to the nearest one. Not the nearest galaxy, not the nearest cluster, the nearest single star, a little over 4 light years away. Consider what that means. Our absolute speed record, the crown jewel of every rocket we have ever fired, held without pause for a full human lifetime, cannot carry one person out of their own solar neighborhood, and it grows stranger the closer you look. That record speed is only about 0.06% of the speed of light. Even if we could somehow hold it forever, aimed straight outward into the dark, reaching that nearest star would take not 1 lifetime, and not 10 lifetimes, but roughly 7,200 years. That is around 99 human lives, laid end to end, one generation quietly handing the ship to the next, just to arrive at the closest door in the entire cosmic neighborhood. Our fastest is not merely slow. Against the distances that actually separate the stars, it is very nearly standing still. Now here is what will quietly rearrange everything you think you know about the size of a single human life. The distance you can cross is not truly limited by your machines, not by your engines, not by your fuel. It is limited by something far stranger, something woven into the fabric of time itself. And inside that limit, hidden in the very same equations that seem to trap us here, there is exactly one loophole, one narrow door through which a single person could, in principle, cross millions of light years inside one waking lifetime. But that door asks a price, and the price is not money, and it is not fuel, and it is not the danger to your fragile body. The price is everyone you have ever loved, and the whole world you left behind, aging into dust and silence, while you are still young enough to remember their faces. We are going to walk toward that door slowly tonight. We will begin with what our real machines have actually crossed, the true distances, the honest numbers, nothing exaggerated. Then we will follow the engineers who spent their lives dreaming of something faster, and at last we will arrive at that single loophole physics allows, and the quiet impossible bargain it asks in return. If you find comfort in slow, careful journeys through the real physics of the universe, the kind that reward your attention yet forgive you completely if you drift off somewhere along the way, do me a small favor and press that like button and subscribe. It genuinely helps this channel grow, and it lets me keep making these long, deep dives for you. So settle in now. Let the lights go low. Make yourself warm and comfortable, and let your breathing slow to match the pace of these words. There is nowhere you need to be, and nothing you need to do, except drift with me out past the edge of everything familiar. Let's begin. Consider first the fastest a living human being has ever traveled. Not a probe, not a machine with no pulse and nothing to fear. A person, with a beating heart and a family somewhere below, watching the sky and waiting. That record has stood now for more than half a century, and it belongs to 3 men, Thomas Stafford, John Young, and Eugene Cernan, the crew of Apollo 10, who on the 26th of May, 1969, came falling home from the moon at 39,897 kilometers per hour. That is very nearly 11 kilometers in every single second. In the time it takes you to draw one slow breath, they had crossed the length of an entire city and left it far behind them. Hold that picture in your mind for a moment. 3 ordinary human beings, made of the same soft and breakable stuff as you, moving faster than any of our kind ever has, before or since. No crewed mission has gone faster in all the years that followed. 55 years have passed, and that single number still sits at the very top of the list, undisturbed. Not because we forgot how it was done, not because the engineers who came after them were any less daring or less brilliant, but because no one, in all the decades since, has been given a reason urgent enough to fling human bodies outward at that speed again. The moon was the errand was completed, and the record simply stayed exactly where those 3 men left it, hanging in the dark, waiting for a successor who never arrived. The journey that carried them out was far gentler than the plunge that brought them home. Reaching the moon took the Apollo crews roughly 3 days, coasting outward at something closer to 3,700 kilometers per hour for most of the long way there. 3 days to cross 250,000 miles of emptiness. It felt, at the time, like humanity had finally stepped off its own doorstep and out into the wider dark. And in a real sense, it had. Yet the moon, for all the distance it seems to hold, is the very nearest thing to us in the entire sky. It is not the street. It is not the city. It is not the country waiting somewhere beyond the hills. It is the single worn stone step just outside the front door. And it took us 3 days to reach that step. Then something changed in the story. We stopped sending our fragile bodies outward and began sending our machines instead. And the machines could do the one thing no crew ever could. They could simply keep going. On the 5th of September, 1977, a spacecraft called Voyager 1 lifted away from Earth and never stopped. It carries no passengers. It feels no fear, no boredom, no ache of homesickness in the long quiet years. And precisely because it carries no one, it was free to be thrown outward along a path that no living traveller could have endured, or survived long enough to see the end of. Voyager 1 moves at roughly 17.3 kilometers per second. That is about 62,000 kilometers in every hour, faster than the men of Apollo 10 at their very fastest, and it has held that pace without pause, without rest, without a single moment of hesitation, for nearly 49 years. Think for a moment about what 49 years of unbroken motion actually buys. Voyager 1 now sits something like 172 astronomical units from Earth. 1 astronomical unit is simply the distance from the Earth to the Sun, the span that light itself takes about 8 minutes to cross. So this small patient machine now rests more than 170 times farther from us than the Sun. On the 25th of August, in the year 2012, it crossed a threshold that nothing built by human hands had ever crossed before. It passed through the heliopause, the outer wall of the Sun's influence, at a distance of 121.6 astronomical units, and slipped out into true interstellar space. Not the space between the planets, the space between the stars themselves. And here is where the honest arithmetic begins to press quietly against us. Imagine that you could have climbed aboard Voyager 1 at the very moment of its launch. Imagine an infant strapped in beside those cold instruments, riding outward through the whole of a human life. Suppose you rode it not for 49 years, but for 73, the length of an average human life on Earth today, 73.4 years, the full span most of us are ever given. At Voyager's speed, sustained through every waking and sleeping second of that entire life, you would cover only about 267 astronomical units. You would pass the heliopause. Yes, you would leave the Sun's magnetic reach behind you. But you would still not have crossed even a small fraction of the way toward the next real shore. Not 1/10 of the way. Not 100th. A whole life spent moving faster than any human has moved, and you would arrive nowhere in particular, still deep inside the outermost reaches of the only home our species has ever known. Voyager 1 is not even the last chapter in this quiet escalation. On its heels came faster machines still. A spacecraft called New Horizons swept past distant Pluto in the July of 2015. the closest any craft has ever come to that small and frozen world, moving at something near 84,000 kilometers per hour. It became the fifth machine ever set on a course to leave the solar system entirely, and by the early months of 2026, it had reached roughly 64 astronomical units from Earth. Faster than Voyager, younger than Voyager, and still, in the grand accounting, barely stirring. These are the swiftest things our civilization has ever made, and set against the true scale of the distances involved, they drift like leaves on very slow water. To feel the full size of that gap, hold two journeys side by side. Remember that it took the crew of Apollo 11 about 3 days to reach the moon, coasting at some 3,700 kilometers per hour. Now consider our fastest machine of all, a probe we will return to shortly, moving at its own extraordinary peak. That same trip to the moon, at that peak speed, would take not 3 days, but roughly 35 minutes. 35 minutes against 3 days. The distance did not change. The moon did not move. Only the speed of the thing crossing the gap changed, and it changed by a factor so large that the two journeys hardly seemed to belong to the same universe. This is the shape of every step we are about to take. Each new machine makes the one before it look almost quaint, almost slow, almost like a child's first careful steps across a room. And each new machine, in turn, is made to look small the moment we compare it against the true distances waiting out there in the dark. That comparison is the thread we will follow now, patiently, one number at a time, because the story of how far a human being could travel is really the story of a single number growing, and then being humbled, and then growing again, and being humbled again, over and over, across the whole history of our reaching. It begins with 3 men falling home from the moon at 11 kilometers a second. It moves to a lone machine crossing into the space between stars after half a century of silence. And it does not stop there. Each speed we have ever achieved has felt in its moment like the edge of the possible. Each one felt like enough. Not enough for everything, perhaps, but enough to matter, enough to be proud of. And each one, when weighed against the true gulf between the stars, has revealed itself to be almost nothing at all. Almost, but not quite, standing still. So let us keep walking up this ladder of speed, rung by rung, because the next few rungs are where the story stops being about the past and starts becoming strange. We have seen the fastest a human heart has ever travelled. We have seen the patient machine that outran it and kept going into the dark. Now we come to the fastest thing our species has ever built at all. A spacecraft that moves not at tens of thousands of kilometers per hour, but at hundreds of thousands. A machine that touched a speed no human hand had ever set in motion before. It did not carry a crew. It could not have. No living body could survive what it endures. And even it, the crown of all our engineering, the swiftest object ever to leave this world, is about to teach us the same humbling lesson, one final and unforgettable time. That machine has a name, and the name is the Parker Solar Probe. On the 24th of December, 2024, while much of the world was asleep or gathered around warm tables, it did something no object built by human hands had ever done. It fell toward the sun and reached a speed of 692,000 kilometers per hour. In the older units many of us grew up with, that is 430,000 miles per hour. Written as a rate the body can almost feel, it is a little over 190 kilometers crossed in every single second. Not per minute, not per hour, per second. Consider what that speed would do to the familiar distances of our own lives. Traveling at its peak velocity, the Parker Solar Probe would cross the entire distance from the Earth to the Moon in about 35 minutes. The astronauts of Apollo 11 made that same crossing in roughly 3 days, moving at about 3,700 kilometers per hour. So this one probe, in the time it takes to watch a short film, would cover a gulf that once demanded 3 days of a crew's life. Their food, their sleep, their fear. It is not merely faster than the men who walked on the moon. It is faster by a factor so large that the comparison stops feeling like a comparison at all. This is the reality of the fastest thing we have ever made. It did not achieve that speed by burning some miraculous fuel. It achieved it by falling. The probe was flung again and again past the planet Venus, each pass bending its path and tightening its orbit, until at last it dove to within 3.8 million miles of the surface of the Sun, closer than any craft in history. At that closest point, the point astronomers call perihelion, the immense gravity of the Sun whipped it to its maximum velocity. This was not a single lucky moment either. The probe returned to that same blistering record 3 more times through the following year, on the 22nd of March, the 19th of June, and the 16th of September, 2025, matching its own impossible number with each return. Decades of planning, and a machine that touched the same peak again and again with quiet precision. And here is the first soft catch in the story. That staggering number is not a cruising speed. It is a momentary flash, reached only at the bottom of the dive and only for an instant. Not a speed the probe carries with it out into the dark. A speed the Sun lends it for a single heartbeat and then takes back. Away from perihelion, the same gravity that granted the gift begins to reclaim it, dragging the probe back toward the star. The record velocity is real, and it is measured, and it is ours. But it is a borrowed thing, and it is spent almost as soon as it is earned. Now place that velocity against the only ruler that truly matters out here, the speed of light. 692,000 kilometers per hour sounds like the very edge of the possible. Measured against light, it comes to roughly 0.06% of the speed of light. Not 6%, not even 1%. 0.06%, the fastest object our entire civilization has ever produced. The sum of every equation and every launch and every sleepless engineer moves at a whisper of a fraction of the pace at which the universe itself actually communicates. But let us be generous. Let us imagine something the probe can never truly do. Let us pretend we could take that peak speed and freeze it in place, carry it outward from the Sun without losing a single kilometer per hour, and hold it steady for an entire human life. Recall our budget. The average person alive today can expect to live 73.4 years. So imagine a traveller who is born at the very instant the engine locks to full velocity, and who rides that impossible sustained speed every day of a full lifetime, never slowing, never stopping, until the very last breath. At that pace, the traveller would cross a little over 6 billion kilometers every single year, roughly 40 times the distance between the Earth and the Sun, in each turn of a birthday. Over the whole of those 73 years, the odometer would climb to some 440 billion kilometers. In the language astronomers use for such gulfs, that is nearly 2,900 astronomical units. An astronomical unit being simply the distance from the Earth to the Sun. It is an almost unimaginable journey. And yet, measured in light years, the true currency of the stars, it comes to less than 1/20th of a single light year. So where does a whole lifetime at humanity's absolute top speed actually deposit you? Not among other stars. Not even close to another star. It carries you just to the inner boundary of the Oort Cloud, the vast frozen shell of debris that marks the outermost edge of our own Sun's domain, the distant region where the long comets are born. You would have spent every second of your only life at the fastest speed a human machine has ever reached, and you would arrive still inside your own solar system's outermost porch, still in every meaningful sense, at home. Not lost among the stars, but standing at the far end of your own back garden. And the nearest star? Proxima Centauri sits 4.25 light-years away. Take that same frozen peak speed, that same impossible sustained velocity, and point it directly at that star, and the journey would take approximately 7,200 years. Set that number against a single life, and it becomes almost unbearable to hold in the mind. 99 human lifetimes, laid end to end, one after another, 99 births and 99 deaths, generation handing the voyage to generation across 7,000 years, and only then would the very first traveller finally arrive at the doorstep of the closest star to our own. Not a distant exotic star at the rim of the galaxy, the nearest one, the one next door. This is the same lesson the horses taught, and the steam engines, and the early aircraft, and the Apollo capsules, and the patient voyagers drifting now in the cold. Every rung of the ladder we have climbed, from a galloping animal to a probe kissing the surface of the sun, has raised our speed by orders of magnitude, and every rung, when weighed against the true distance between the stars, has left us essentially motionless. The gap between our fastest machine and the walking pace of a single person is enormous. The gap between our fastest machine and the journey to one neighbouring star is so much larger that the first gap simply vanishes inside it, the way a grain of sand vanishes inside an ocean. And so we arrive at the crushing truth that the whole of this long expansion has been quietly walking toward. The question that opened this journey was a simple one. How far could a single human being actually travel from the Earth within one ordinary lifetime? We have now answered it honestly, using nothing but the machines we have truly built and the speeds we have truly reached. And the honest answer is that a human life spent at the maximum velocity our species has ever achieved would not carry us to another star. It would not carry us even 1/100th of the way. It would not even carry us out of our own solar system's farthest shell. Our fastest is not slow. It is, against the distances that matter, indistinguishable from standing perfectly still. And that leaves us facing a far stranger and far deeper question. If raw speed can never be enough, and it cannot, then the only path by which a human being could ever cross that gulf within a single lifetime must lie somewhere else entirely. Not hidden inside our engines. Hidden, instead, inside the nature of time itself. For almost the whole of our existence, we treated time as the one fact that could never be bargained with. A second was a second. An hour was an hour. The clock on the wall in one city ticked at precisely the same rate as the clock on the wall in another, and no journey, no velocity, no act of will could ever change that. This felt less like a scientific claim, and more like the flaw beneath every other truth. It seemed obvious. It seemed permanent. It seemed like the single thing in all of creation that would never quietly betray us. That confident feeling was wrong. Not slightly wrong. Fundamentally wrong. Time is not a fixed backdrop against which events play out. It is not a river flowing at one steady speed for everyone everywhere forever. Time is something closer to a material, something that can stretch and compress, something that bends according to how fast you move. Once you understand that, the entire question of how far a human being can travel changes shape completely. The barrier was never really distance. The barrier was our assumption about the clock. It is worth pausing to understand why the illusion is so total. Every clock you have ever seen agreed with every other clock. Your watch matched the clock in the train station, which matched the clock in your childhood kitchen, which matched the great clocks in distant cities you have never visited. Nothing in ordinary life ever cracks that agreement, not because time is truly absolute, but because the speeds of ordinary life are so gentle that the differences hide far below anything a human being could ever perceive. We built our entire intuition inside a narrow room, and we mistook the walls of that room for the shape of the whole universe. The person who first saw past those walls was not a famous professor in a grand laboratory. In 1905, a 26-year-old patent clerk named Albert Einstein sat at a desk in the patent office in Bern, Switzerland, reviewing applications for electrical machines. He had no telescope. He had no great instrument of any kind. He had almost nothing but a pencil, a stack of paper, and a willingness to take one strange idea seriously. That idea was simple to state and devastating to follow. The speed of light he proposed is exactly the same for every observer, no matter how fast that observer is already moving. Consider what this means. Imagine you are standing still, and you measure a beam of light racing past you. Now imagine you chase after that same beam at enormous speed, faster than any rocket we have ever built. Common sense insists that the light should now appear slower to you, the way a car beside you on the highway seems to crawl once you match its pace. But the light does not slow down, not by a fraction. It races away from you at exactly the same speed as before, as if your tremendous effort had meant nothing at all. There is a way of picturing this that makes the strangeness feel almost gentle. Imagine that everything in the universe is always moving through a combined budget of space and time, and that the total is always fixed. When you stand perfectly still in space, every part of that budget is spent moving through time, and your clock ticks as fast as it possibly can. When you begin to move through space, some of the budget is quietly borrowed away from your motion through time. The faster you race across space, the less remains for time, and so your clock slows. Move at the speed of light itself, and every last portion of the budget is spent on space, leaving nothing for time at all. Something has to give to make all of this possible. If the speed of light refuses to change, then the things we use to measure speed must change instead. Speed is only distance divided by time. So if the light keeps its speed no matter what you do, then your distances and your minutes must quietly rearrange themselves to protect that one unbreakable rule. This is not a trick of perception. It is not an illusion in the mind of the traveler. It is the deep machinery of reality, and it means that a moving clock genuinely runs slow. The faster you move relative to someone else, the slower your time flows as seen from their point of view. Sit in a chair, and your clock and their clock agree. Walk across a room, and a difference appears, though it is so unimaginably tiny that no human sense could ever notice it. Board an aircraft and fly across an ocean, and the gap grows, still far too small to feel, yet now large enough that our finest instruments can catch it. This effect has a name. It is called time dilation, and it is not a theory waiting to be tested. It has already been measured. In 1971, two researchers named Joseph Hafley and Richard Keating decided to weigh time directly. They took cesium atomic clocks, the most precise timekeepers ever built, and they bought ordinary seats on ordinary commercial airliners. Then they flew those clocks around the entire world, first heading east, then heading west, while identical clocks stayed behind on the ground. When the travelers landed and the readings were compared, the flying clocks and the resting clocks no longer agreed. The difference was measured in billionths of a second, far too small for any person to feel. But it was there, exactly where the equations had promised it would be. Think carefully about what that experiment proved. The clocks did not disagree because one was broken or poorly made. They disagreed because time itself had passed at different rates for each of them, not because of some flaw in the machinery, but because motion through space genuinely trades against motion through time. The clocks carried aboard those airliners returned home very slightly behind the ones that had stayed still. Not younger in appearance, not younger in feeling, younger in the most literal and physical sense the universe will allow. This is the doorway. It is small, almost insultingly small at the speeds we can reach, but it is a genuine opening in what had seemed a solid wall. If motion can slow a clock at the speed of a passenger jet, even by a few billionths of a second, then motion can in principle slow a clock by years, by centuries, by unimaginable stretches, if only the motion is fast enough. The wall between a human lifetime and the distant stars was never truly built of miles. It was built of seconds. And seconds, it turns out, are negotiable. Now here is the part that matters for our journey to the stars. At the speeds of aircraft, and even at the speeds of our fastest spacecraft, this effect is almost nothing. It is real, and it is measurable, and it changes the reading on the clock. Yet the change is so small that it could never carry a human being across the gulf between stars within a single life. To feel time bend in any meaningful way, you cannot travel at the speed of a jet, or a rocket, or even the fastest probe our spaces has ever flung toward the sun. You must travel at a speed that begins to rival light itself. Even then, the doorway opens slowly. Push a spacecraft to 1/10 of the speed of light, a velocity so far beyond our engineering that nothing we have ever built comes remotely close, and time dilation still barely stirs. At that blistering pace, the traveller's clock runs slow by a factor of only about 1.005. Cross the more than 4 light years to the nearest star at that speed, a voyage of roughly 42 years, and the traveller arrives having aged less than a single year fewer than everyone left behind on Earth. 42 years of a life poured out into the dark, and time dilation hands you back less than one of them. Picture what that voyage would actually feel like from the inside. You would board your ship as a young person, and for more than 4 decades you would live an entire ordinary life within its walls. You would sleep and wake tens of thousands of times. Your hair would grey, your hands would age, your body would run through its full allotment of years, exactly as it would have on the ground. And when you finally arrived, the friends you left behind would have aged those same 42 years and a little more, having missed you by less than a single birthday. At 1/10 of light speed, the nearest star remains a place you can reach only by spending nearly your whole life to get there. This is the quiet cruelty hidden in the mathematics. At the speeds we can imagine, time dilation is a rounding error. It is a curiosity for physicists, a footnote in a textbook, a difference measured in the flicker of an atom. The effect is real at every speed, but it only becomes a true passage, only becomes a way through, when you approach the speed of light so closely that the ordinary rules of arithmetic seem to bend and break. There, at the very edge of what the equations permit, the numbers stop being gentle. There, a single year of your heartbeat can outlast whole centuries. There, one human lifetime can, in principle, stretch across distances that light itself needs thousands upon thousands of years to cross. To see how far that passage can open, we have to follow the equations past the speeds we know and toward the speeds we can only dream of. We have to imagine a ship that does not simply reach a great velocity and coast, but one that pushes, steadily and relentlessly, closer and closer to the speed of light. What happens to a human clock then is not a rounding error. It is a transformation so severe that it reshapes the meaning of the word distance, and with it, the meaning of the word home. The transformation has a name, and the name is deceptively plain. Physicists call it the Lorentz factor, a single number that describes how much a moving clock slows relative to a clock left behind. At the speeds of everyday life, this number sits so close to 1 that no instrument you own could ever measure the difference. A car on a highway, a bullet in flight, a spacecraft leaving Earth, all of them experience time dilation, and all of it is unimaginably small. The effect is not absent, it is only hidden, and yet it is not hidden from everything. In 1971, 2 physicists named Joseph Hafele and Richard Keating did something that sounds almost too ordinary to matter. They bought tickets on commercial airliners. They carried with them a set of cesium atomic clocks, instruments so precise that they measure the vibration of atoms billions of times each second. They flew these clocks around the entire world, once heading east and once heading west, and then they compared them against identical clocks that had stayed on the ground. The flying clocks and the stationary clocks no longer agreed. The difference was measured in billionths of a second, but it was exactly the difference the equations had predicted. Time had bent, ever so slightly, for the clocks that moved. Consider what this means. The strangeness at the heart of relativity is not a theory waiting for proof. It is a measured fact, confirmed by ordinary clocks on ordinary planes, carried by 2 men holding boarding passes. If a passenger jet flying a few hundred miles per hour can pull 2 clocks out of step, then the principle is real, and the only remaining question is one of degree. How much faster must you go before that trickle of lost time becomes a flood? The answer is deeply counterintuitive. You might expect that travelling at say 1/10 of the speed of light would slow your clock by roughly 1/10. It does not. At 1/10 of light speed, a velocity of nearly 67 million miles per hour, the Lorentz factor is only about 1.005. Over a voyage of 42 years to the nearest star, a traveller moving at that blistering pace would age less than a single year fewer than everyone left on Earth. Not decades less, not even one full year less. The universe does not begin to offer its bargain at 1/10 of light speed. It barely acknowledges that you are moving at all. This is the cruelty hidden in the mathematics. The reward for speed is not linear. It does not grow steadily as you accelerate. For almost the entire climb from a standstill toward the speed of light, the clock refuses to bend in any way you would notice. Even 90% of light speed still buys you only a modest slowing. The real transformation waits at the very end of the scale, in the last thin sliver of velocity that separates the possible from the forbidden. As you push from 90% toward 99, and from 99 toward 99.9 and beyond, the Lorentz factor does not creep upward. It erupts. It climbs without any ceiling at all, racing toward infinity as your speed approaches the speed of light and never quite arrives. Picture it as a wall you can lean against, but never break. The closer you press to the speed of light, the harder the wall pushes back, and the more richly it rewards you for pressing. Each additional fraction of a percent costs enormously more energy than the last, and yet each additional fraction of a percent folds time more violently than all the fractions before it combined. The passage to the stars is real, but it opens only in that final punishing sliver of speed, the part of the scale that human engineering has never touched and may never touch. Now imagine a ship that lives inside that sliver. Not a ship that reaches a great velocity and then drifts, the way our probes drift now, but a ship that never stops accelerating. Imagine that it pushes forward with a steady, gentle force, exactly the force you feel standing on the surface of the Earth. One gravity. Enough to hold a cup of water to a table, enough to let a human body live and breathe and sleep without strain, day after day, year after year. That gentle push, sustained without pause, would carry the ship closer and closer to the speed of light, and the Lorentz factor would rise and keep rising, and the clocks aboard would fall further and further out of step with the clocks of home. And here the mechanism stops being an abstraction on a page and becomes something a body could feel. For the traveller aboard such a ship, nothing would seem strange. Your heartbeat would keep its familiar rhythm. Your meals would come at their familiar hours. You would age, ordinarily, at the ordinary rate, 1 second per second, exactly as you always have. The ship would feel like a quiet room with a floor beneath your feet. That is the deception at the center of it all. From inside, the miracle is invisible. You would have no sense that anything was being stretched, or bent, or lost. The change would show itself only when you looked back. The Earth you left would not be waiting for you, unchanged, the way a house waits for a traveller to return. It would be racing ahead through time while you crawled through it. Every year you spent aboard, the world behind you would spend far more, and the gap would widen faster the longer you travelled. The people you loved would not simply grow older, they would live their whole lives, and their children would live theirs, and generations you would never meet would rise and fade, all in the span of what felt to you like an ordinary voyage. Not because you travelled through space, because you travelled through time and left them behind inside it. This is the passage the equations promise, and it is genuine. It is not a trick or a loophole in the ordinary sense, but a straightforward consequence of the way the universe is built, verified by atomic clocks carried onto aeroplanes more than half a century ago. The stars, the ones our fastest machines would need thousands of years to reach, could in principle be reached within a single human life. The distance does not shrink, the traveller does. Time itself becomes the vehicle. And the price of that vehicle is written in a currency no one has ever truly agreed to pay, because the fare is not measured in fuel, or in years, or in miles. It is measured in everything and every one you would have to leave behind. That is the shape of the mechanism, a door that opens only at the very edge of light and asks for the whole of your world in exchange for passage through it. What that passage would actually demand, in energy, in engineering, in raw human daring, is a question that grows stranger and heavier the closer you hold it to the light. And it is a question we are now ready to hold very close indeed. So people held it close, not poets, and not dreamers filling notebooks with impossible sketches, but working engineers with slide rules, pencils, and the patience to carry a calculation all the way to its bitter end. Long before anyone spoke of folding the universe under acceleration, a smaller and more stubborn question was already sitting on their desks. Could we build the machine at all? Could human hands, using physics we already understood, assemble a vessel that might cross the gulf to another star inside a single human life? The answer, arrived at again and again across the last 70 years, was a strange and unsettling yes. A yes with conditions. A yes that asked for almost everything we had. Consider what this means. The impossibility we have been circling is not, in the end, an impossibility of imagination. On paper, the road to the stars has already been drawn. It has been drawn carefully by serious people, checked and rechecked against the known laws of nature. The obstacle is not that we cannot conceive of the machine. The obstacle is the sheer crushing weight of what the machine would cost to build, to fuel, and to survive. And the first group of people to draw that road in real detail did so in Britain, over the course of 5 patient years. Between 1973 and 1978, a group of engineers working under the banner of the British Interplanetary Society undertook something no one had ever seriously attempted. They set out to design an actual starship, not a fantasy, not a shape from a film, but a machine specified down to its fuel and its structure, a vessel that could be costed, weighed, and criticized. They called it Project Daedalus, after the craftsman of old myth who built wings to escape a prison. The name was not chosen lightly. The prison, in their case, was the solar system itself, and the walls of it were made of nothing but distance. What they designed was a 2-stage fusion rocket of almost unbelievable scale. Its total mass came to roughly 54,000 tons. To appreciate how staggering that figure truly is, consider that the overwhelming bulk of it was never meant to arrive anywhere. It was fuel, and the ship existed mostly to carry the fuel that carried the fuel. This is the tyranny that governs every rocket ever conceived. You do not simply add speed, you add propellant to reach that speed, and then more propellant to move the propellant, and the numbers climb toward the monstrous with every increment of velocity you demand. And yet the reward on paper was extraordinary. Daedalus was designed to reach 12% of the speed of light. In plain terms, that is 36,000 kilometers every second. It is a velocity more than 180 times faster than the Parker Solar Probe at its record best. And the Parker Solar Probe is the fastest object our species has ever made. The target was Barnard's star, roughly 5.9 light-years away. The projected travel time was approximately 50 years. 50 years. A working career, a number that fits, just barely, inside a single human lifetime. Sit with that for a moment. The same crossing our real machines measure in tens of thousands of years, this design proposed to make in 5 decades. Voyager 1, our fastest actual traveller beyond the planets, would need something on the order of 75,000 years to reach a star nearer than Barnard's. Daedalus proposed to reach one that is farther, and to do it before its own engineers grew too old to read the data it sent back. The gap between what we have flown and what we have drawn is not a matter of degree. It is a matter of kind. One is a horse, the other is a bullet. But the design has its own limitation, and it is a cruel one. Daedalus could never stop. It carried no way to slow itself down. It would cross those 5.9 light-years at a full 12% of light speed, and then tear straight through the target system in a matter of hours. Gathering everything it could in one blistering pass, before the star fell behind it forever. This is the quiet horror buried in the arithmetic. Slowing down costs exactly as much as speeding up. To arrive gently, to enter orbit, to linger and study and perhaps to stay, you must carry a second engine as hungry as the first, and pay the whole staggering fuel bill twice over. So the engineers chose the only honest option available to them. They built a machine that could reach another star, but only by agreeing never to arrive at it in any human sense of the word. Consider what that would feel like if you were somehow aboard. You would spend 50 years crossing an ocean of emptiness toward a single point of light, and on the day you finally reached it, you would have only that day. A few hours of frantic looking, and then the light would shrink behind you, and you would carry on into a darkness even deeper than the one you left. The destination is not a place you go to, it is a place you pass. That is the price the flyby demands, and it is written into the very equations that make the journey possible at all. Now here is the detail that unsettles most. Daedalus was not even the first serious attempt to reach the stars with real hardware. 15 years earlier, on the other side of the Atlantic, a different group had already sketched a machine that might have carried people, not just instruments, and might have done it with the technology of its own decade. The mathematics become even more disturbing when you learn how old the possibility actually is. The project was called Orion, and it was studied in earnest between 1958 and 1965. Its method was so audacious that it still sounds like something invented to frighten people rather than to fly them. Orion would be propelled by detonating nuclear devices behind the craft, one after another, riding the shockwave of its own controlled explosions out into the dark. Where every other rocket sips its fuel, Orion would ride the most violent energy release humanity had ever learned to make, and it would do so deliberately, rhythmically, thousands of times over the course of a voyage. It was the closest thing to harnessing a war for the purpose of travel that anyone has ever taken seriously. And the projected performance was almost beyond belief for its era. On paper, an Orion vessel could reach somewhere between 9 and 11% of the speed of light. A robotic 3-stage version was estimated to reach the nearest star in under 50 years, using nothing more exotic than the fission technology already sitting in the arsenals of the 1960s. Read that sentence again, slowly. The means to send a machine to another star within a single lifetime may already have existed, in principle, more than half a century ago. We did not lack the physics. We lacked the will, the money, and any sane reason to detonate several thousand nuclear devices in the name of exploration. Here is the problem though, and it is the same problem that haunted Daedalus. That headline speed belongs to a machine that never has to stop. The moment you ask Orion to carry human beings, everything changes, because human beings expect to survive the arrival. A crewed mission needs to decelerate, and deceleration doubles the burden, and so the practical velocity falls to roughly 4.5 to 5.5% of the speed of light. That halving sounds modest. It is anything but. At 5% of light speed, the nearest star, Proxima Centauri, slips back to something like 85 years away, and 85 years is longer than the global average human life. The robotic probe fits inside a lifetime. The crewed ship, needing only to slow down and live, does not. The very act of wanting to survive the journey pushes the destination back beyond the edge of your own years. This is the pattern that repeats across every honest design our species has ever produced. There is always a version that works, and it is always the version that gives something up. Give up stopping, and you can reach the stars but only glimpse them. Give up passengers, and you can send a machine but no one to witness what it finds. Give up the demand for speed, and the journey stretches past the length of the life that undertakes it. Each proposal is a bargain, and each bargain quietly removes the one thing you most wanted to keep. To appreciate how relentless this truly is, consider that these were not the fantasies of amateurs. Project Orion drew on some of the finest physicists of its age. Project Daedalus drew on the accumulated craft of a national engineering society. Both worked from real numbers, real materials, real energy budgets, and both arrived, by entirely independent roads, at the same austere conclusion. The stars are reachable. They are simply reachable at a cost so total that no nation on Earth has ever been willing to pay it, and no engineer has ever managed to lower it below the threshold of the unthinkable. For a long stretch of the 20th century, that seemed to be the whole of the answer. Bombs and fusion, both monstrous, both fitting inside a lifetime only by refusing to slow down. The dreams of the mid-century were dreams of raw power, of pushing harder, of burning more. Then, in our own century, a very different kind of proposal appeared. It did not ask how much energy a starship could carry. It asked whether the starship needed to carry any energy at all, or whether the push could be left behind on Earth entirely, and the vessel made so small that a gram of matter might be flung toward Proxima on a beam of concentrated light. That idea would arrive with famous names attached, a fortune pledged, and a promise of the nearest star within a working career, and it would run headlong into a problem of its own. The name it carried was Breakthrough Starshot, and it arrived in 2016 with a weight of reputation behind it that few scientific proposals have ever enjoyed. Behind it stood the physicist Stephen Hawking, the investor Yuri Milner, and the technologist Mark Zuckerberg, and behind their names stood a pledge of $100 million. The idea was elegant to the point of audacity. Do not build a great ship. Build a chip. Shrink the spacecraft until it weighs no more than a single gram, mount it on a mirrored sail thinner than a sheet of foil, and leave the engine on the ground. On Earth, an array of lasers with a combined output of 100 gigawatts would fire in perfect unison, striking the sail with a wall of concentrated light and driving the tiny craft forward. Not for hours, not for days. For a few brief minutes the beam would pour into the sail, and in those few minutes a gram of matter would climb to 1/5 of the speed of light. That is 20% of the fastest thing that exists. And at that velocity, the distance to Proxima Centauri, 4.25 light-years of emptiness, collapses from the 72 centuries a Parker-class probe would demand into something almost human. 20 to 30 years. A single working career. Consider what this means. A young scientist who launched the fleet in her early 30s might, if she was patient and fortunate, still be alive when the first faint signal came home. The signal itself, crawling back at the speed of light, would take more than 4 years to return across that gulf. But she would be there to read it. For the first time in the entire history of the idea, the nearest star had been pulled inside the boundary of a single lifetime. Not by burning more fuel, not by building something larger, but by making the traveller almost nothing at all, and lending it the power of the whole planet for a handful of minutes. Here is the problem. The elegance of the idea was matched, point for point, by the brutality of its engineering. A sail that thin must survive being struck by 100 gigawatts of light without tearing, warping, or simply vaporizing in the first instant. The lasers must fire in a coordination so precise that they behave as a single beam across kilometers of ground, and that beam must find and hold a target the size of a postage stamp as it recedes into the dark. The craft, once launched, carries no engine of its own, and so it has no way whatsoever to slow down. It does not visit Proxima Centauri. It crosses the entire star system in a matter of hours, gathering what it can in that fleeting pass, and then it is gone forever into the emptiness beyond. And even setting all of that aside, the fundamental achievement, accelerating a gram-scale sail to 1/5 of light speed, has never been demonstrated. Not at full scale, not at small scale, not once. The reputation and the fortune could not, in the end, purchase a solution. By September of 2025, Breakthrough Starshot had been placed on indefinite hold. Of the $100 million pledged, only about $4.5 million had ever been spent. The rest was never called upon, because the problems it was meant to solve had refused to yield. This is the sober reality of the fastest proposal humanity has ever seriously entertained. It was not defeated by a lack of money, and it was not defeated by a lack of brilliance. It was defeated by the sheer physical difficulty of doing the one thing that would make the stars reachable within a life. Other minds had walked up to the same wall from a different direction. The physicist Geoffrey Landis proposed a laser-powered interstellar sail of his own, one designed not for a gram of matter, but for a genuine payload, driven to roughly 1/10 of the speed of light. At that pace, Alpha Centauri lies about 43 years away, still inside a lifetime, still just barely within reach. And if the sail were made larger, the numbers grew almost tantalizing. A sail 320 kilometers across could bring the arrival down to just over 12 years. A sail 965 kilometers across could cut it to under 9. Consider the audacity of those figures. Under 9 years to another sun. But consider too what they require. A mirrored structure the width of a small country, and a laser infrastructure to push it that lies far beyond anything that has ever been built, or that anyone knows how to build. The destination is close, the machinery to reach it is not. Step back then from the specific proposals and look at the pattern they trace. Whether the vessel is a 54,000-ton fusion behemoth, or a fleet of fission bombs, or a gram of silicon riding a beam of light, the serious engineering of the last 70 years keeps arriving at the same narrow country. To reach the nearest star inside one human lifetime, a craft must travel at somewhere near 1/10 of the speed of light. That is the threshold. Below it, the journey stretches past the length of any life, past centuries, past the span of recorded history. At it, or just above it, the nearest star finally comes within reach of a single set of eyes. So let us take that threshold seriously and follow it to its consequence. Imagine a ship that has somehow solved every problem and cruises at a steady 10% of the speed of light. At that pace, Proxima Centauri is roughly 42 years away. A traveller who departs at 20 could arrive before old age. And here we brush for the first time against the strange machinery that lives inside the speed of light itself. Because when you move that fast, time no longer passes for you exactly as it passes for those you left behind. The universe, as we will see, keeps a different clock for the traveller than for the home world. But at 1/10 of light speed, that difference is almost nothing. The time dilation factor is only about 1.005. Understand what that number is telling you. Across the entire 42-year voyage to Proxima Centauri, the traveller would age less than a single year less than the people waiting on Earth. Not a decade less. Not a lifetime less. Less than 1 year. The clocks disagree, but they disagree by a whisper. At the speeds our best proposals can imagine, relativity is real, and it is measurable, and it is also almost beside the point. The traveller and the world she left behind grow old together, separated by a matter of months across 4 decades. And this is where the story could comfortably end, with a sober verdict: the nearest star is barely reachable, the difference in clocks is trivial, and the universe beyond remains sealed away behind distances that no lifetime can cross. That whisper of a difference, 1.005, seems to close the case rather than open it. It suggests that time dilation is a curiosity, a footnote, a thing that matters only to atomic clocks and physicists. That impression is wrong. Not slightly wrong, fundamentally wrong. Because that factor of 1.005 does not stay small. It is the first gentle stirring of an effect that grows without limit as speed climbs toward the speed of light. And hidden inside the very equations that make it seem so trivial lies a loophole so profound that it changes what the word distance is even allowed to mean. To find that loophole, we have to travel back to a small office in a modest city, to a man whose job had nothing to do with the stars. The year was 1905, the place was the patent office in Bern, Switzerland, and the man bent over the desk, reviewing applications for electrical devices and mechanical toys, was 26 years old. His name was Albert Einstein. He had no telescope, no laboratory, no funding, and no title that would impress anyone. What he had instead was a question that would not leave him alone, and a willingness to trust that question even when it led somewhere absurd. The question was simple to ask and almost impossible to accept. What would you see, Einstein wondered, if you could ride alongside a beam of light? Everyday intuition gives a confident answer. Ride fast enough beside anything, a train, a bird, a bullet, and it appears to slow, to hang beside you, to freeze. So a beam of light, chased at its own speed, should freeze too, should hang in the air as a motionless ripple. But every experiment ever performed said this was impossible. Light did not slow when you chased it. It fled at exactly the same speed no matter how fast you ran. Not approximately the same speed, exactly the same speed, for every observer, in every direction, always. This should have been a minor technical puzzle. Instead, it was a crack in the foundation of reality. Because if the speed of light never changes, no matter how the person measuring it is moving, then something else has to give. Speed is only distance divided by time. If everyone measures the same speed for light while moving at wildly different speeds themselves, then the two things we always assumed were fixed, distance and time, cannot both be fixed. One of them must bend. And Einstein followed that logic to its unforgiving conclusion. Not one of them bends. Both of them do. This is the idea that most people never truly absorb, even after hearing it 100 times. Ask anyone what time is, and they will describe it as a river that flows at the same rate for everyone, everywhere, a universal clock ticking in the background of the cosmos, indifferent and absolute. That picture feels obvious. It feels like bedrock. It is also completely wrong. Not wrong in some small correction at the third decimal place. Wrong at the root. There is no universal clock. There is no single shared present moment stretching across the universe. Time is not a river the whole cosmos floats down together. Time is personal. It belongs to the thing that carries it, and it runs at a rate that depends on how that thing moves. For most of human history, no one noticed this, and for a very good reason. The effect only becomes visible near the speed of light, and nothing in ordinary experience comes anywhere close. A person walking, a horse galloping, a jet aircraft crossing an ocean, all of them move at such a tiny fraction of light speed that the bending of time is far too small to feel, far too small to see, far too small to matter to a life lived on the ground. The universe hid this truth, not because it is rare, but because our speeds are slow. We were simply never fast enough to catch the machinery of reality in the act. And yet the effect is real, and we have caught it. Not in theory, not on a chalkboard, in the physical world, with instruments, on an ordinary day. In 1971, two researchers named Joseph Hafele and Richard Keating decided to test Einstein's strange claim in the least glamorous way imaginable. They did not build a rocket. They bought airline tickets. They carried a set of cesium atomic clocks, the most precise timekeeping devices then available, onto commercial passenger flights, and they flew those clocks around the world, first heading east, then heading west, sitting in ordinary seats aboard ordinary aircraft. Back on the ground, an identical set of clocks stayed behind, ticking quietly in the laboratory, waiting. When the travelling clocks came home, the scientists compared them against the ones that had never left. The clocks no longer agreed. The difference was staggeringly small, measured in billionths of a second, far too fine for any human sense to register. But it was there, and it was the size that Einstein's equations had predicted decades earlier. The clocks that had flown had, quite literally, experienced a different amount of time than the clocks that had stayed. Not because they were broken, not because of vibration or temperature or altitude alone, but because motion itself changes the rate at which time passes, and the faster you move, the more it changes. Consider what this means. Time dilation is not a thought experiment or a science fiction conceit. It is a measured fact, confirmed with clocks you could buy and aeroplanes you could board, sitting in the same cabin as vacationers and business travelers who had no idea they were flying through a demonstration of the deepest secret in physics. If moving a few hundred miles per hour around the planet is enough to bend time by billionths of a second, then the door Einstein opened is not locked, it is merely heavy. And the question becomes not whether time can be stretched, but how far it can be stretched if we could only push hard enough on that door. This is where the trivial little number from before returns and reveals its true nature. At 1/10 of the speed of light, the factor by which time stretches is only about 1.005. We already saw how underwhelming that is. Over a voyage of decades, it amounts to a difference of months. It looks like a rounding error, a footnote, a reason to dismiss the whole idea. But that number is not a fixed quantity. It is a single point on a curve, and the shape of that curve is the most important thing in this entire story. Because the curve does not rise gently and then level off. It rises gently, and then it turns, and then it climbs, and then it climbs faster, and then it soars toward infinity as your speed approaches the speed of light. The name physicists give to this stretching factor is the Lorentz factor, and its behavior is unlike almost anything in everyday life. Double your speed from a crawl, and the factor barely moves. Push from 1/10 of light speed toward half of it, and the factor begins to lift its head. But as you close in on the last few percent before light speed, the factor stops behaving like a number and starts behaving like a wall that recedes forever. At 90% of light speed, time aboard the ship runs at less than half the rate of time back home. Press higher, and the gap widens without mercy. There is no ceiling. There is no maximum value. The nearer you approach the speed of light, the more violently the traveller's clock diverges from the clock of everyone left behind, and that divergence has no upper limit at all. Sit with the strangeness of that. It means the barrier that has crushed every hope in this story so far, the impossible vastness of interstellar distance, is not the fixed and final wall it appears to be. It is fixed only for those who stay behind, only for the patient watchers on Earth counting the years. For the traveller moving fast enough, the distance itself shrinks. The space between the stars, from the ship's own point of view, contracts, folds, collapses towards something crossable. The light years do not go anywhere. They are still out there, still vast, still measured in the trillions of kilometers. But they are vast for Earth, not for the ship. And that distinction, invisible at the speed of a horse or a jet or even a space probe, becomes everything near the speed of light. Here is the first glimpse of just how much everything changes. At 1/10 of light speed, Proxima Centauri lies roughly 42 years away, a full human career of travel, a voyage that consumes most of a working life. But that is the slow way, the gentle push, the modest fraction of light speed. Suppose instead you could accelerate steadily, continuously, at a rate that feels exactly like standing on the surface of the Earth, the comfortable pull of ordinary gravity pressing you into your seat, hour after hour, year after year, never stopping. Under that steady push, the ship keeps gaining speed, the Lorentz factor keeps climbing, and the space ahead keeps contracting. And by the ship's own clock, the nearest star arrives not in 42 years, not in a decade, but in about 3.5 years. 3.5 years of a single life, to cross a gulf that would take our fastest probe 75,000. That is the loophole, not a trick of engineering, not a faster engine, but a rearrangement of the very meaning of distance and time, hidden in plain sight inside equations a young patent clerk scribbled more than a century ago. The universe never promised that the light years would be the same for everyone. It only promised that the speed of light would hold firm. Everything else, every distance, every duration, every clock, was always negotiable, always personal, always waiting to bend for anyone who could move fast enough to make it bend. Consider what this means. The claim that a single lifetime could cross to a star in 3.5 years while the same crossing devours 75,000 years for a machine we launched in the 1970s, sounds less like physics and more like a magician's promise. It sounds like a cheat. It sounds like the kind of thing that must collapse the moment anyone tests it against the real world. And this is exactly the misconception worth dismantling, slowly and completely, before we go any further. Ask almost anyone whether time is the same everywhere, and they will answer without hesitation. Of course it is. A second is a second. An hour is an hour. The clock on your wall, and the clock on a distant mountain, and the clock aboard a ship racing between the stars, all tick in perfect agreement, marking out the same universal moment for everyone, everywhere, always. That confident answer is wrong. Not slightly wrong. Fundamentally wrong. Time is not a fixed river flowing at one rate for all of creation. Time is local. Time is personal. Time is something each moving thing carries with it, running fast or slow depending on how that thing moves through space. There is no master clock hanging in the sky above the universe, no single authoritative moment that binds Earth and ship and star together. Every clock keeps its own honest time, and when two clocks move differently, they simply disagree, and both of them are correct. The reason this feels impossible is that our intuition was built at walking speed. We evolved crossing savannas, not slicing through the fabric of space at a meaningful fraction of light. At the speeds a human body has ever known, the disagreement between clocks is so unimaginably small that no sense we possess could ever detect it. So we concluded, reasonably, that time was absolute, because in the narrow slice of reality we inhabit, it very nearly is. The error is not stupidity, it is scale. The truth was always there, folded into the numbers, waiting at velocities we simply never reached. And here is the part that turns speculation into fact. This is not a thought experiment. The bending of time has been verified experimentally, directly, using instruments and journeys that anyone can understand. In 1971, two scientists named Joseph Hafele and Richard Keating carried out an experiment so simple it borders on the absurd. They took cesium atomic clocks, among the most precise timekeeping devices humanity has ever built, and they bought seats on ordinary commercial airliners. They flew those clocks around the entire world, first heading east, then heading west, while identical clocks stayed behind on the ground. Not in a laboratory sealed off from the world, not in some exotic machine buried underground, on the same passenger planes that carried tourists and travellers across the ocean. When the flying clocks came home and were compared against the ones that had stayed still, they no longer agreed. The difference was measured in mere billionths of a second, a quantity so small it means nothing to a human life. But it was there. It was real. It matched the predictions of Einstein's equations to within the precision of the instruments themselves. The clocks that had moved had genuinely experienced less time than the clocks that had stayed, not because of a malfunction, not because of a measuring error, but because time itself had passed differently for the ones in motion. A young patent clerk in Bern had written down, more than 60 years earlier, exactly how much those airborne clocks would fall behind, and reality obeyed him to the decimal. Now hold that result in your mind and stretch it. At the crawling pace of an airliner, the effect is a handful of billionths of a second, invisible, meaningless to anything but the finest atomic clock. This is the crucial point that our slow-speed intuition can never grasp on its own. The bending of time is not switched on at some magical velocity. It was operating in that airliner. It is operating in the car you drive, in the plane you have flown, in your own body as you walk across a room. It has always been operating. It is simply too faint to notice until you approach the speed of the thing that sets the universe's pace. And that is where the loophole stops being a curiosity and becomes a door. The gap between two clocks does not grow smoothly with speed, adding a little more disagreement for each mile per hour. It grows in a way that starts imperceptible and then, as you climb toward the speed of light, races toward the infinite. At a modest 1/10 of light speed, the sort of velocity our boldest engineering studies have dared to imagine, the stretching of time is still gentle. The factor is barely more than 1. A traveller crossing to the nearest star at that speed would age less than a single year fewer than the people left behind. A rounding error across a voyage of decades. Not enough to matter, not enough to feel, just enough to prove the effect is genuine and waiting. But the mathematics do not stay gentle. As velocity presses closer and closer to the speed of light, the multiplier that separates the ship's clock from the world's clock does not level off. It has no ceiling. It climbs without limit, steeper and steeper, until a single tick aboard the ship corresponds to 100 ticks on Earth, then 1,000, then numbers with no comfortable name. The closer you push to that final speed, the more violently the two timelines tear apart. And it is inside that runaway, inside that unbounded climb, that the entire question of this journey quietly changes its shape. Because the barrier was never really the distance. We have spent this whole exploration measuring the gulf to the stars in numbers that crush the imagination, tens of thousands of years, hundreds of thousands of years, spans that swallow every civilization that has ever lived, and every one that ever will. But those are Earth's years. Those are the numbers written on the master clock we now know does not exist. The traveller carries a different clock, and that clock does not care how many centuries pass in the world behind it. The loophole does not shorten the road, not 1 kilometre of it. The more than 40 trillion kilometres to the nearest star remain exactly that many kilometres. What bends is not the space. What bends is the time you spend inside it. Consider the strangeness of that. 2 travellers could leave Earth on the same day. One flies to the nearest star and back at a gentle fraction of light speed, and returns having aged, honestly, most of a human lifetime. Another flies the same round trip pressed hard against the speed of light, and returns having aged only a handful of years, stepping off the ship still young, still strong, while the first traveller has grown old. They covered the same distance. They obeyed the same laws. The only difference was how firmly each one pushed against the ceiling of light, and that single difference rewrote how much life each one spent along the way. The road was identical. The price in years was not. So the honest reframing of our entire question is this. We began by asking how far a human could travel from Earth in one lifetime, and we assumed, without ever questioning it, that a lifetime was a fixed and universal thing, roughly 73 years for everyone, the traveller and the watchers alike. That assumption is the one that was quietly wrong all along. The traveller's lifetime and the world's lifetime are not the same lifetime. Under a steady push, the faster you go, the more of the universe you can fold into the years your own heart is allotted. And if that push could somehow be sustained, not for the minutes of a rocket burn, but for the long patient decades of an entire voyage, the reach of a single human life stops being measured in the outer shells of our own solar system. It begins to be measured in something almost too large to say out loud. That something is a table, not a spacecraft, not a blueprint, not a mission patch stitched with a launch date. It is simply a column of numbers, worked out from equations a patent clerk in Bern set down more than a century ago. And it is one of the strangest documents physics has ever produced. It describes a single ship under a single, almost absurdly simple condition. The condition is comfort. Imagine a vessel that can hold a steady push of 1 gravity, not a violent burn, not the crushing weight of a launch that flattens a pilot into their seat. Simply the ordinary pull you feel right now, sitting still. The exact force that keeps your cup on the table and your feet on the floor. On a ship accelerating at 1 gravity, you would not float. You would walk its corridors as if they were rooms in a house back home, your weight familiar, your footsteps unremarkable. This is the gentlest possible way to cross a universe. It is also, as it happens, close to the fastest way a human body could ever bear to travel. Hold that push, and something begins to happen that everyday life gives you no way to picture. Speed accumulates. Within the first year, the ship is already moving at a substantial fraction of the speed of light. It keeps pushing. And here the ordinary arithmetic you were taught in school quietly stops working. You cannot simply keep adding speed until you overtake light itself. The universe does not permit it. Instead, as the ship presses closer and closer to that final velocity, the extra energy stops becoming speed and starts becoming something else. It becomes time, not the ship's time. The traveler's clock keeps ticking at its ordinary human pace, 1 second per second, a heartbeat for every heartbeat. It is the relationship between that clock and the clocks left behind that begins to bend. This is the effect that everyday experience conspires to hide from you. At the speeds a human life actually contains, the walk to the door, the drive across a country, the flight across an ocean, the bending is real but unimaginably small, buried so far down in the decimal places that no ordinary sense could ever feel it. It is the same effect the flying clocks measured, only whispering instead of shouting. Push a body close enough to light, though, and the whisper becomes the loudest fact in the sky. What was a rounding error at the speed of a jet becomes the entire story at the speed of a starship. Consider what this means for the distances we have been struggling against all this time. At a steady 1 gravity, the nearest star, Proxima Centauri, 4.25 light-years away, arrives in 3.53 years of shipboard time. Not 73 years, not 7,000. 3.5 years, less than the time it takes to earn a degree, and the traveller steps out beneath another sun. Push on. The Pleiades, that small blue cluster 444 light-years from here, the little knot of stars our ancestors named and used to mark their seasons, is reached in 11.88 years of the traveller's life. Less than 12 years to cross a gulf that light itself needs 4.5 centuries to span. The table does not stop there. It barely slows. Keep the push steady, and the entire disk of our galaxy begins to fall away behind. The galactic center, 26,000 light-years distant, the crowded, blazing heart around which every star you have ever seen slowly turns, is reached in 19.89 years of ship time. Consider what that sentence contains. A person could be born, grow up, and arrive at the center of the Milky Way before their 20th birthday, having crossed a distance so vast that the light leaving there tonight will not reach Earth until human civilization is 26,000 years older than it is now. The traveller does it in under 2 decades. The mathematics do not care how impossible that feels. The equations were written down, checked, and confirmed, and they say what they say. Now push past the edge of our own galaxy entirely. Andromeda, the great spiral, the nearest major galaxy to our own, 2.5 million light-years across the empty dark between islands of stars, is reached in 28.6 years of shipboard time. Read that number slowly. Not the nearest star, not the far rim of our own galaxy, not the scattered dwarf galaxies that trail the Milky Way like moths around a lamp. An entirely separate galaxy, a trillion suns of it, a wheel of light so distant it appears to the naked eye as a single faint smudge, reachable in less than 30 years of a human life. A traveller who departed at 30 could arrive before 60, still working, still curious, still recognisably themselves. And here the beautiful arithmetic reveals its price. While the traveller ages those 28.6 years, the universe outside does not keep pace. It races. The measure of that mismatch has a name, the Lorentz factor, and on the journey to Andromeda, it climbs to roughly 1.3 million. Not 1.3, not 13, not 13,000, 1.3 million. For every single year the traveller spends aging inside that ship, more than 1 million years unspool across the cosmos left behind. By the time the vessel reaches Andromeda, 28.6 years older, approximately 2.5 million years will have passed on the Earth it departed. The traveller crosses the gap between galaxies in the span of a single career. Earth crosses the gap between one human species and the next. Sit with what that number does to everything you know. 2.5 million years ago, on the Earth that would be waiting, there were no humans as you would recognize them. Our ancestors were walking upright on an African plain, chipping the first crude edges onto stones, their brains a fraction the size of yours. If one of those creatures had somehow boarded such a ship and pushed off at one gravity, it would step out at Andromeda 28 years older, and everything that has ever been called human history, every language, every city, every war and cathedral and symphony and forgotten name, would have arisen and would still be arising in the time it was gone. That is not a figure of speech. That is the literal accounting of the equations. The traveller experiences one ordinary lifetime. The home world experiences the entire arc of a species, from the first sharpened flint to whatever comes after us. There is one more line on the table, and it is the one that is genuinely difficult to hold steady in the mind. Keep pushing at one gravity, and the edge of the observable universe itself, the farthest boundary of everything light has ever had time to show us, 93 billion light years from one side to the other, comes within reach in 45.3 years of shipboard time. 45 years. A single working life, from a first job to an ordinary retirement. In that span, the traveller could in principle cross the entire visible cosmos, from our small blue world to the last galaxies flickering at the limit of sight, the ones whose light set out before the Earth had cooled into a crust. The universe, in the strange bookkeeping of a steady push, is not endless after all. It is roughly 45 years wide, measured by a human heart. This is the deepest and quietest terror the physics has to offer. Not that the universe is too large to cross, but that it is, in a sense no one expected, crossable, and that the crossing costs you everything you leave behind. The distance was never the true wall. Space folds. Under a steady enough push, the light years compress toward the traveller like a long road seen at speed, the far things rushing near, the whole enormous map drawing inward until galaxies come to sit within the reach of a single life. What does not fold, what cannot be argued with or engineered around or softened by any amount of comfort, is the time on the other side. The ship's clock and the home clock have parted ways forever. The gap between them only widens the farther the traveller dares to go. Everything said so far has treated this ship as though it simply exists, as though a vessel that holds one gravity for decades were something you could requisition, board and fly. It is not. The table of ship time distances is arithmetic, and the arithmetic is sound, checked against the very same relativity that keeps the satellites above your head telling accurate time. But arithmetic is not an engine. To hold one gravity for 28 years, to keep pressing a human body and its ship ever closer to the speed of light with no rest and no coasting, demands something the elegant little table politely declines to mention. It demands energy, and the amount of energy hidden inside that innocent Lorentz factor of 1.3 million is where the dream, so weightless and clean on paper, meets a wall built into the deepest structure of reality itself. Consider what that wall is made of. It is not a wall of engineering, not the kind a bolder generation might climb with a stronger alloy or a cleverer design. It is a wall written into the arithmetic of motion itself. Every additional sliver of speed toward light costs more than the sliver before it, and the cost does not rise gently. It rises without ceiling. The same Lorentz factor that folds the journey to Andromeda into 28.6 years of shipboard life is the factor that inflates the fuel required to get you there. One number gives the gift. The identical number names the price, and the price climbs faster than any tanker vessel could ever carry. Yet even the energy, monstrous as it is not the cruelest thing hidden in these equations. There is a second cost, and this one is already paid the moment the engines light. It is paid in people. It is paid in the world you leave behind. Set the fuel aside for a moment. Imagine the impossible ship exists, that it holds one gravity for decade after decade without complaint. It still cannot give back the thing it quietly takes. Time on the homeworld does not pause while you travel. It runs, and it runs fast. Return to Andromeda, 2.5 million light-years across the dark. The traveller who reaches it under one steady gravity ages 28.6 years. A young person departs. A person in late middle age arrives. That part is almost gentle. But on Earth, in that same interval, roughly 2.5 million years have passed. Not 2.5 million years of history in the human sense, with names and dates and remembered wars. 2.5 million years of the kind that erases languages, drowns coastlines, and turns whole species into fossils. The traveller crosses a single lifetime. The homeworld crosses an epoch longer than the entire span of the human story so far. Sit with the shape of that number. Everyone the traveller ever knew is not merely dead. Their descendants are dead. The descendants of their descendants, across 100,000 generations, are dead. The city of departure is not ruined. It is gone, its very stone recycled into soil. The language spoken at launch survives nowhere, in no mouth, in no record any living thing could read. The traveller does not return to a changed home. There is no home to return to. Not a home that aged. Not a home that moved on. A home that has been comprehensively forgotten by time itself. A place that exists now only inside a single aging skull aboard a ship that left before the memory of it could fade. Notice how the gap itself grows as the destinations recede. Proxima Centauri under one gravity arrives in 3.53 years of shipboard life, and only a little more than 4 years pass on Earth. That is a fair trade, a near-matched pair of clocks, a journey a person could make and still come home to grandchildren who remember their face. The Pleiades cluster, 444 light-years away, arrives in under 12 shipboard years, while 444 years drain away at home. The centre of our galaxy, 26,000 light-years through crowded fields of stars, arrives in under 20 shipboard years, while 26,000 years pass beneath the departed sky. Andromeda, 28 shipboard years, 2.5 million years at home. The divergence does not add, it multiplies, and it multiplies without any kindness at all. And Andromeda is not the far edge of this cruelty. It is barely the middle of it. Push the same engine harder, hold the same single gravity longer, and the shipboard clock stretches further still. The far boundary of everything we can see, the edge of the observable universe, arrives in 45.3 years of shipboard time. Less than a single human lifetime. A person could be born, could grow, could age, and could cross the entire visible cosmos, all inside one biological span. This is the reality the equations encode and everyday experience hides. At that final speed, the Lorentz factor is no longer 1.3 million. It is roughly 7.1 billion. While the traveller ages 45 years, 7.1 billion years elapse in the universe outside. That is longer than the Earth has existed. It is longer than the sun has burned. A traveller who set out to touch the edge of the visible universe would return, if return were even a word that still meant anything, to find the sun itself dead, the solar system dark and cold, the entire theatre of human life not merely ended, but geologically deep in a past no instrument could ever recover. Stack the losses and let their full weight settle. Not a lost friend, not a lost city, not a lost civilization, not even a lost species. The traveller bound for the cosmic edge would lose the star that made every warm day they ever felt, and the planet that held every footprint they ever left, and the very era of the universe that contained the possibility of anything called human at all. The journey is technically survivable. The homecoming is not survivable in any sense that matters, because there is no home, no era, and no witness left to receive it. And here is the quiet horror underneath all of it. None of this feels dangerous. That is what everyday experience conceals. The same law that scatters a traveller across 7 billion years is the law measured in 1971 with cesium clocks carried aboard ordinary airliners, and the difference then was a matter of billionths of a second. It is the law that keeps the satellites above your head honest. Your body lives inside this equation every moment of every day, and it hides from you completely, because at the speeds a life actually moves, the effect is far too small to feel. Reality does not warn you, it simply keeps the accounting, patient and exact, at every velocity from a walking pace to the brink of light, and reveals the true size of the bill only when a traveller dares to demand the whole of it. So the dream of one gravity is real and false at once. Real, because the arithmetic holds, because the universe truly will fold itself for anyone able to pay. False, because the payment is arranged so that no one can ever collect the prize and keep the things that made it worth wanting. You may cross the cosmos, or you may keep your world. The equations permit exactly one, never both. This is the deepest cut of the whole subject, deeper than distance, deeper than speed. The barrier was never only out there in the empty light years. The barrier runs through the traveller, splitting the clock in their chest from every clock they left behind, which returns us at last to the wall the elegant little table declined to mention. Time is one price, paid in everyone you love, but before a single second of that folded shipboard time can be spent, there is the other price, the physical one, the energy hidden inside that Lorentz factor and the fury of the space the ship must pass through. To hold one gravity for decades is to hurl a human body toward light itself, and the universe does not let mass approach that speed gently, nor cheaply, nor safely. The fuel, the radiation, the sheer brutal cost of the crossing, all wait on the far side of the dream like a toll no treasury on earth has ever been able to name. And it is there, in the raw ledger of energy and the storm of particles at the very edge of light, that the last and hardest wall is waiting to be counted. Begin with the energy, because energy is the wall that does not negotiate. Time can be folded, and we have seen that it folds beautifully, a lifetime stretched across galaxies inside a single beating chest. But the folding is not free. Every fraction of the speed of light you buy must be paid for in motion, and motion has a currency, and that currency is measured by the same factor that bends the clock. The Lorentz number that compresses your calendar is the very number that inflates your fuel. They are not two separate problems. They are one problem, wearing two faces, and the face that grants you the years is the same face that demands a fortune no world has ever held. Consider what this means at the gentle end of the ladder first. At 1/10 of the speed of light, the time dilation factor is only about 1.005, and the crossing to Proxima Centauri takes roughly 42 years. That is a modest bend in the calendar and a modest bill. The energy required to push a vessel to 1/10 of light speed is already staggering by every human standard, far beyond the total output of our machines. Yet it is a number you can at least write down and stare at. It has a beginning and an end. It sits inside the realm of the merely enormous. Now climb to where the universe actually folds. To reach the Andromeda Galaxy in 28.6 years of shipboard time, holding one gravity the entire way, the traveller must ride a Lorentz factor of approximately 1,300,000. That is not a small adjustment to the previous bill. The kinetic energy of a moving mass does not rise politely with speed. As the Lorentz factor climbs, the energy climbs with it, so a factor near 1,300,000 does not mean a fortune slightly larger than before. It means a fortune larger by a factor beyond any accounting we possess. The energy needed to carry a single human body to that velocity lies incomprehensibly beyond every known source of power in existence, not beyond our current reactors, not beyond our largest bombs, beyond the sum of everything we have ever learned to burn or split or fuse. This is the crushing reality of relativistic travel. The time dilation that seemed like a gift, that promised to fold 2.5 million years of cosmos into a young person's stride, was never a discount. It was an invoice written in a language we struggle even to read. The equations that offered the loophole also stamped the price at the bottom, and the price is the loophole. You cannot have the compressed decades without paying the energy that compresses them. The very mercy of the mathematics is its cruelty, and even that catastrophic figure is only half of the true cost. To accelerate is one expense. To stop is another expense exactly as large. A ship that reaches a target at relativistic speed and does not decelerate does not visit that target. It annihilates itself against it, or it flashes past in an instant and continues into the dark forever, a corpse at enormous velocity. To actually arrive, to slow from a fraction of light speed to something a human body and a landing can survive, requires as much energy spent braking as was spent building the speed in the first place. This is the tyranny hidden inside every honest interstellar plan. You do not carry fuel for the journey, you carry fuel for the journey. And then you carry the fuel that will slow that fuel, and then you carry the fuel that will accelerate the fuel that slows the fuel. The propellant needed does not add, it multiplies. A practical relativistic mission that intends to stop needs roughly twice the propellant of one that merely departs, and because propellant must itself be accelerated, that doubling does not sit quietly at the surface. It compounds downward through every stage until the numbers curl away into absurdity. Here is the problem stated plainly. The dream of one lifetime spanning galaxies is not defeated by a missing invention. It is defeated by arithmetic that grows faster than any invention could ever hope to grow. We are not one clever engine away from Andromeda in 28 years. We are separated from it by a wall of energy that rises the moment we approach, and rises faster the closer we come, so that the finish line recedes precisely because we run toward it. But energy is not the only toll waiting on the far side of the dream. There is a second wall, quieter and in its own way more intimate, because it does not threaten the treasury, it threatens the body. Space between the stars is not truly empty. A cubic centimeter of air at sea level on Earth holds roughly 25 billion molecules, a crowd beyond counting. A cubic centimeter of interstellar space might hold a single atom. To a stationary object, that lone atom is nothing at all, a solitary speck drifting in a vastness of nothing. But the traveller is not stationary. The traveller is moving at a fifth of the speed of light, or more, and at that velocity the meaning of that single atom changes completely. This distinction matters enormously, because at 1/5 of light speed the ship does not drift through the sparse hydrogen of the void, it slams into it. Each thin, harmless atom of interstellar gas arrives at the hull not as a mote, but as a bullet of radiation, a high-energy particle striking with a violence borrowed entirely from the ship's own speed. The emptiness that looked like mercy becomes a continuous storm. What was a whisper of gas to a slow probe becomes, at relativistic velocity, a relentless sleet of ionizing particles washing across the front of the vessel, hour after hour, year after year, sterilizing electronics and shredding living tissue. The faster you go, the harder the emptiness hits you. Speed does not carry you above the danger. Speed is the danger, and so the engineers who dream of these crossings must add a third impossible weight to a ship already impossibly heavy. They must add shielding, mass enough to absorb that particle storm and protect the fragile cargo behind it. But shielding is mass, and mass must be accelerated, and accelerating mass demands energy, and the energy was already the wall we could not pay. The radiation problem does not stand beside the fuel problem, it feeds it. Every kilogram of shield you add to survive the sleet of light is another kilogram you must hurl to relativistic speed, and then, if you ever wish to stop, another kilogram you must somehow bring to rest. The shielding that saves the traveller helps ensure the traveller can never leave. The two walls lean against each other, and together they hold. To appreciate how total this barrier truly is, consider that we have not yet solved it even at the smallest imaginable scale, for the smallest imaginable payload, with no human aboard at all. In 2016, 3 names the world knows well: the investor Yuri Milner, the physicist Stephen Hawking, and the entrepreneur Mark Zuckerberg announced breakthrough Starshot, with a pledge of $100 million. The ambition was not to send a person. It was not to send a probe the size of a car, or a suitcase, or even a hand. It was to send a chip, a gram-scale sail, thinner than paper, pushed to 1/5 of the speed of light by a ground-based laser array, drifting to Proxima Centauri within 20 to 30 years. The most modest interstellar craft ever seriously proposed, carrying nothing but a camera and a whisper of electronics, weighing less than a coin, and by September of 2025, that project was placed on indefinite hold. Of the $100 million pledged, only about $4.5 million had ever been spent. The engineering did not yield. Even a fleck of matter, even a gram accelerated by the largest laser humanity could imagine building, remained an unsolved problem after nearly a decade of the finest minds and real money aimed directly at it. Not because the dreamers lacked ambition, not because the physics forbade it outright, but because the gap between the equation on the page and the machine in the world proved wider than $100 million could span, and wider, it seems, than patience could outlast. This is the honest ledger, then, laid open at last. The relativistic loophole is real. The mathematics does not lie. A human being could, in principle, ride one gravity of acceleration across the folded decades and see Andromeda while still young. That door genuinely exists in the architecture of the universe. But standing in the doorway are the two figures we have finally counted. One holds a bill for energy beyond every source we know, doubled for the crime of wanting to stop, compounded past the edge of language. The other holds a storm of light that grows fiercer the faster you flee it, and demands a shield that only makes the first bill worse. Between them, the door that physics leaves open is a door that engineering has never once managed to walk through. Not for a person, not for a probe, not even for a single gram of matter with a camera taped to its chest. And yet the door is still a door. It did not close. That is the strange, thin, persistent thread we are left holding as the numbers fall silent. The universe did not say never. The universe said not yet, and not cheaply, and not without a price paid in energy and radiation and, waiting behind both of them, in time itself, in everyone left standing on a shore that ages while the ship does not. Which is where the arithmetic finally runs out, and something older than arithmetic has to take its place. But arithmetic does not surrender all at once. It leaves a few last entries before it goes quiet, and each one is heavier than the one before it. Consider the first. To reach the Andromeda galaxy in 28.6 years of a traveller's own life, the ship must climb to a Lorentz factor of roughly 1,300,000. That number is not a speed. It is a measure of how completely the traveller has torn free of ordinary time. And to reach it, the vessel must carry a store of energy so vast that no reservoir we have ever named comes close. Not the output of a power plant, not the yield of a single bomb, not the burning of an entire world. The kinetic energy locked inside one human body moving that fast lies incomprehensibly beyond any source of power we know how to build. And the ship must supply it not once, but continuously, second after second, for years. Now add the cruelty hidden in the arrival. To slow down is not free. Deceleration demands the same energy as acceleration, poured out in the same merciless quantity, only in reverse. A mission that merely wants to reach somewhere and stop must therefore carry roughly twice the propellant of emission content to fly past forever. And propellant is not weight you add gently. Every extra kilogram you bring to slow down is a kilogram you must first accelerate, which demands more fuel, which adds more mass, which demands more fuel again. The problem does not grow, it compounds. It feeds on itself the way a debt feeds on its own interest, until the ship you imagined becomes a mountain, and the mountain becomes a moon, and the moon still is not enough. This is the crushing reality of wanting to stop, not the reality of speed. Speed, in the cold logic of the equations, is almost generous. It is the stopping, the arriving, the standing still at the far shore that physics punishes without mercy. And even if you found the energy, The universe has one more toll to collect, and it collects it in radiation. Empty space is not empty. Between the stars drift thin veils of hydrogen, a single atom here, a single atom there, so sparse that a human standing among them would notice nothing at all. But raise your speed to 1/5 the speed of light, and those harmless drifting atoms cease to drift. They arrive. Each one strikes the hull as a bullet of pure energy, a sleet of high-velocity particles that never stops, that comes from dead ahead in every moment of the voyage, that would pass through thin metal and soft tissue alike. To survive it, the ship must wear a shield. And the shield, of course, is mass. More mass to accelerate, more mass to decelerate, more fuel to move the shield that protects the fuel. The storm of light grows fiercer the faster you flee it, and the faster you flee, the more of everything you must carry to endure it. Consider what all of this has done to our brightest attempt. Breakthrough Starshot did not dream of moving a human. It dreamed of moving a chip, a sail, a gram of matter no heavier than a folded note. It asked only for 1/5 of light speed, for an object small enough to rest on a fingertip, and it was backed by a pledge of $100 million and some of the most serious minds alive. By the year 2025, that project had been quietly set aside, placed on indefinite hold, with only about $4.5 million of the pledge ever spent. Not because the people lost interest, because the engineering, even for a single gram, even for no passenger at all, refused to yield. The door physics leaves open is a door that the richest, most ambitious effort of our century could not push open by so much as a crack. So this is where the threads gather, and they gather into a knot rather than a bow. On one side stands the energy, a bill written in numbers with no name, doubled the moment you decide you would like to survive the arrival. On the other side stands the radiation, a headwind of pierced atoms that only worsens as you succeed. And braided through both of them, quiet and patient, waits the third price, the one that cares nothing for shielding or fuel: time. For the traveller bound for Andromeda, 28.6 years pass inside the ship. Outside it, on the world left behind, roughly 2.5 million years pass instead. Pushed to the very edge of the visible universe, and the traveller spends 45.3 years, a single working life, while 7.1 billion years bury the Earth they departed. The ship returns. There is nothing left to return to. And here is the thin thread, the one we said we would keep holding. The door did not close. Every one of these prices is real, and every one is monstrous, but not one of them is a law forbidding the journey. The equations do not say it cannot be done. They say only what it would cost. That is a different kind of sentence. A wall says never, a price says not yet. The difference between them is the entire narrow space in which human hope has always lived. The same space that once separated a person watching birds from a person crossing an ocean by air. But hope of this shape is a strange thing to hold. It offers the stars and asks, in exchange for the world. It says yes, you may stand one day beneath the light of another galaxy, and it says the price of that standing is every face you have ever loved, aged and gone and turned to dust and then to something with no name, millions of years before your ship even begins to slow. The 73.4 years granted to an average human life is the one quantity in all of this that relativity cannot bend on the departure shore. The traveller's clock can be slowed almost to stillness. The clocks of those who stayed cannot. They keep the ordinary time. They run out on schedule, which means the real barrier was never truly the energy, and never truly the radiation, and never truly the arithmetic of fuel that eats itself alive. Those are engineering. Those are, in the long patience of a species, perhaps solvable. The barrier that does not move is smaller and closer and quieter than any of them. It is the length of a single life, and the fact that every other life keeps aging while one of them is spent reaching outward. That is not a problem you shield against. That is not a problem you burn fuel to escape. It is the shape of the question itself, and it turns us at last away from the machines and back toward the strange and restless animal that keeps on asking. Consider what that animal actually is. It is a body that runs for roughly 73.4 years and then stops. It is a mind housed inside that body, aware of its own deadline, and unwilling to accept the walls the deadline builds. Every machine in this story was an argument against those walls. Every number was our spaces leaning against the bars of its own biology and measuring, very precisely, how little room they leave. That act of measuring is the strangest thing we do. No other creature we know of has ever stood at the edge of its own brief life and asked how far it could throw itself into the dark before the dark closed over it again. We are the species that measures its own prison. We do it calmly. We do it with atomic clocks and horn-shaped antennas and fusion rockets sketched on paper by people who knew they would be long dead before the first bolt was ever machined. There is something almost unbearable in that patience. A person builds toward a journey they will never take, for a destination they will never see, on behalf of a descendant who does not yet exist. Not because the reward is theirs, it never will be, but because the reaching itself seems to be the thing our kind cannot stop doing. So the question that opened all of this returns now, changed. How far could a human actually get from Earth in one lifetime? We have the answers. At the speed of our fastest machines, still tangled in the outer shells of our own solar system. At a modest fraction of light speed, perhaps the nearest star, if we ever build the engines. At a steady one gravity of acceleration, the whole universe, but only for the one who travels, and only at a price paid entirely by everyone left behind. The physics is settled. What remains is not a physics question at all. It is a question about what a life is for. Perhaps the reaching is worth any cost. Perhaps a single human, stepping out of a ship beneath the light of another sun, would justify every sacrifice that carried them there. Every clock left running on a departure shore that aged into dust while they slept between the stars. Perhaps the species that refuses to stay put is the only kind worth being, and the ache of everything left behind is simply the fare, paid gladly, for passage into the deep. Or perhaps the human spirit requires belonging more than it requires distance. Perhaps a life is measured not by how far it travels, but by whose hands are holding it at the end. And a journey that returns you to a dead and silent world has taken from you the only thing that ever made the going matter. Both of these can be true at once. That is the quiet cruelty of the whole arrangement, and also its strange grace. The universe does not force the choice, it simply lays the two truths side by side and lets them stand there, unreconciled, the way they have stood since the first person looked up and wanted to be somewhere else. The traveller who reaches Andromeda in 28 years of shipboard time is not wrong to have gone. The ones who stayed and lived and died in ordinary time, watching the sky where the ship vanished, are not wrong to have stayed. There is no equation that ranks them. There is no experiment that settles it. These questions have no universal answers. Different people will make different choices, and every one of those choices will be defensible, and none of them will be complete. Some would trade their whole world for a single glimpse of another. Some would not trade a single ordinary evening at home for all the light years in the catalogue. You already know, if you are honest, which of those two people you are closer to being. You have known it for longer than you have been listening tonight. The remarkable thing is not that the answer differs from person to person. The remarkable thing is that a soft biological creature, with a lifespan barely longer than 7 decades, is in a position to be asked the question at all. Think of what is already out there, deciding nothing, feeling nothing, and yet standing in for all of it. In November of 2026, nearly 49 years after it left the launch pad, Voyager 1 will become the first object human hands have ever built to reach a full light day from Earth, roughly 25.9 billion kilometers into the dark. A command whispered toward it on a Monday morning will not arrive until the middle of that day, and the machine's faint reply will not reach us until Wednesday. Say good morning to Voyager, and the answer comes back 2 days later. That is the size of the silence we have already learned to speak across. not metaphorically, measured in the plain arithmetic of light. And Voyager keeps going, powerless now to change its course, carried by the momentum of a decision made in the 1970s. In roughly 40,000 years it will drift to within about 1.6 light-years of a dim star called Gliese 445, and that pass, that near miss across an ocean of emptiness, will be the closest any object our species has ever made will ever come to another star. Not in our lifetimes. Not in the lifetimes of any civilization we could recognize. 40,000 years from now, when whatever we become has forgotten the language these words are written in, a battered probe with a golden record bolted to its side will slide past a stranger's sun and keep on falling. That is the farthest fingerprint the cosmos will ever hold of us. A quiet handoff, in the dark, to no one. Hold that image against the other one, the one relativity offers. At a steady 1 gravity of acceleration, the far edge of the observable universe lies only about 45.3 years of shipboard time away. A single human life, spent inside a single accelerating ship, could in principle cross a cosmos that stretches something like 93 billion light-years from end to end. The whole thing. Every galaxy the largest telescopes have ever found, folded down into the span of one career, one marriage, one childhood remembered from the far side of an unthinkable gulf. The universe is not, in the strictest technical sense, too large to cross in a lifetime. That is the loophole. That is what the equations quietly promised all along. But the same equations that open that door hold it shut with the other hand. The traveller crosses the universe in 45 years. The universe, meanwhile, ages by billions. There is no round trip. There is barely a one-way ticket that anyone at home could survive the waiting for. So we are left with these two objects, both of them real, both of them ours. A slow machine that will need 40,000 years to merely graze the outskirts of one neighbouring star, and a theoretical ship that could touch the boundary of everything before its pilot's hair turns fully grey. The distance between those two facts is the exact shape of our predicament, and we are the only creatures alive who can see both ends of it at the same time. That is the thing worth sitting with, in the last quiet stretch of all this. We are small. We are astonishingly, almost comically small, set against the numbers we have spent these hours counting. A body that lasts 7 decades, a top speed, in the flesh, of not quite 40,000 kilometers an hour, unbroken for more than half a century, a reach, with our best machines, that has not yet cleared the porch light of our own front door. By every measure the cosmos offers, we barely register. And yet the register itself, the measuring, the knowing of exactly how small we are and precisely how far the walls stand, is a thing the universe did not have until we arrived to do it. The stars did not know their own distances. The light from Proxima Centauri had been crossing those 40 trillion kilometers for 4.25 years, indifferent, unwitnessed, until a creature on a small wet planet caught it, and named it, and worked out to the decimal how long its own machines would need to follow it home. The cold did not know it was cold. The dark did not know it was dark. It took an animal with a 73-year clock and a refusal to look away to turn a silent, unlabeled cosmos into a place with a map and a scale, and a set of impossible, beloved destinations penciled in along its edges. So the honest answer to how far a human could get is not a number. It never quite was. The numbers we have are true, and they are humbling, and they are worth knowing down to the last significant figure. But underneath them sits something the arithmetic cannot reach. Perhaps that is the part worth carrying with you into sleep. Perhaps the distance is the gift, and not the wound. Perhaps a spaces that can measure the exact dimensions of its own cell, down to the final significant figure, has already done something that no cell can hold. Or perhaps the ache is the whole point. Perhaps the reaching matters more than the arriving, and a creature that could brush the far edge of everything without longing would not be human at all. We do not have to choose between these two truths tonight. The universe does not require us to settle the question in this lifetime, or in the 99 lifetimes it would take our fastest machine to drift as far as the nearest star. These are questions without universal answers. Different people, lying in different rooms under the same indifferent sky, will answer them differently, and every answer will be true for the one who gives it. Some of you will hear these numbers and feel a door quietly close. The stars are too far. The clock of 73 years is too short. The price the universe asks for passage is one that no fuel, no engine, no century of patient effort can pay. And some of you will hear the very same numbers and feel a door swing slowly open. Because for the first time in the long history of our kind, the far edge has a distance written beside it. Because a wall once measured stops being infinite and becomes merely enormous. Which of those two feelings rises in you is not for anyone else to decide. It was never a question with a single answer. It is yours, and it always was. So consider, one last time, where you actually are. You are resting on a small, warm, wet world. One that has been turning quietly for close to 4.5 billion years. Inside a galaxy of a few 100 billion suns. Inside an observable universe that stretches roughly 93 billion light-years from one edge to the other. Light itself, the fastest thing that exists, would cross only 73 4/10 light-years in the entire span of your life. Within that small bright bubble sit perhaps 2,000 stars and 1,400 systems, a scattering of unseen worlds you will never touch. Every one of them older and more silent than any story you have ever been told. You are smaller than the smallest rounding error in that arithmetic, and yet you are the thing that is doing the arithmetic. That is not a sentence of despair, it is very nearly the opposite. The cold does not measure itself. The dark keeps no ledger of its own depth. The 93 billion light-years have no idea that they are wide. It took something as fragile and as brief as you, something with a 73-year clock and a stubborn refusal to look away, to lift its eyes from that short life and give the whole vast, indifferent structure a name, a scale, and a handful of impossible destinations penciled along its rim. In November of this year, Voyager 1 becomes the first object human hands have ever built to stand a full light day from home, 25.9 billion kilometers out, still whispering faintly back across that gulf. Still ours. In roughly 40,000 years it will drift within a little over a light and a half of another sun, carrying the fingerprint of a single warm afternoon on Earth, farther than any living thing will ever travel. We did that. Half blind, half a lifetime at a time, burning chemical fire and gravity and patience, we did that. So rest now. Let the numbers settle where they fell. The Oort Cloud will still be out there in the morning, and the nearest star will still be 4.25 light-years away, and the edge of the observable universe will still sit 45 years of a traveller's own heartbeat beyond the last thing anyone has ever seen. Somewhere in the mathematics, a steady push of one gravity still folds that entire visible universe into 45 years of a single traveller's life, waiting, in principle, for an engine we have not yet learned to build. None of it is going anywhere. Neither, tonight, are you. And that is enough. To have measured the prison is already to have half escaped it. To have named the distance is already to have crossed some quiet portion of it, in the one vessel that has never once failed us, which is the human mind lying still in the dark, reaching. The stars are out of reach tonight, and yet we measured the reaching, named the dark, and drew the map, and the map is ours.